Okay, so as we start our second section of this lecture, we understand that there are three different definitions of acid and base. And as we already pointed out for the rest of the chapter, we're going to separate the Bronsted-Lowry definition and Arrhenius definition altogether. Specifically, when we talk about the basicity of the water, or the solution, we use OH minus. That concept, of course, comes from Arrhenius definition. So here I just like to point out, so we won't get a surprise, and you find out how come sometimes we use BL's definition for the acid base, and sometimes we use Arrhenius definition for the acid base. All right, so remember from BL's definition, we realized water can be an acid and a base at the same time. So people might come up with a crazy idea to say, what about water molecule react with water molecule? One is acid, one is a base. All right, let's see what happened. So a proton is transferred. So from this, we noticed that we got a two pair of conjugates right here. So H2O for acid, its conjugate base is OH minus. For second water, it's acting as reactant base, so its conjugate acid will be H3O plus. Okay, so this equilibrium is very interesting, and it is the foundation of all acid-base equilibrium, as we soon will see. This equation has to be long investigated before the whole concept of acid and base. So this equilibrium has its own unique name called self-dissociation, autoionization, and on and on. So these are the two most popular names for such equilibrium. Since it's equilibrium, so we can write a Kc for it. And I'd like to remind you, so water here is a liquid. Remember, pure liquid and solid shouldn't be any part of a mathematical expression of a Kc. So Kc here is just the production of H0 plus and OH minus, their concentration at equilibrium. All right, just like its name has a very different way from the rest of equilibrium, so this Kc is also called ion product constant, so we call it Kw. And for water, Kw is a constant. It's a 1.0 times 10 to the negative 14 at 25 degrees Celsius. And this is the one of the most important concepts that we're going to apply to in this chapter, as well as the next chapter. Because when we talk about acid and base, most likely it happens in the water. So as long as we have water, Kw applies no matter how. Why Kw is so important? That is because Kw contains two key components as we label as either acid or in the base. So as we can see, H3O plus is the acid. OH minus is what we call as base. So from this equation, it's obvious we can come up with a conclusion that if we increase the concentration of H3O plus, it will suppress the concentration for OH minus. Remember, the product of these two winds up with a constant. So the concentration for one is inversely proportional to the other. So this is something I want you guys to understand. But what's even more important conclusion I like to draw here is both species, hydronium and hydroxide, they are present and coexist in all aqueous systems. So that means even for the acidic solution, we have OH minus for certain concentration. In very strong base like sodium hydroxide, there always going to be a very small amount of hydronium exists in the solution. So how do we understand this? Which one's dominant, right? So if we talk about the hydroxide, since hydroxide is a dominant or more concentrated, so it shows more basic than acidic, so we call it base. So this Kw is one of the most important concepts that support most of our calculation throughout the chapter and the next chapter as well. All right, since we have introduced the new equilibrium, okay, the auto-ionization of water, okay, since it's equilibrium, so we can set up an ice table to figure out what the equilibrium concentration will be for these two ions. All right, so as we set up the ice table, we start with the initial concentration. Remember, liquid does not include it in the math. So as for initial, before ionization, so the concentration of the two ions must be 0. As for change, as the equilibrium goes, they both will increase a certain amount. Remember, the stoichiometry between the two ions is 1 to 1. So that is why it's plus x and plus x for both. As the equilibrium concentration, so that's going to be x, because 0 plus x equals to x. Apply that to the mathematical expression of a Kw. So we realize it's going to be x squared equals to 1.0 times 10 to the negative 14th. All right, so we take square root of the Kw, so we understand equilibrium concentration of both ions are exactly the same, which is 1.0 times 10 to the negative 7th molar. Okay, so here it's a moles per liter. So the concentration of these two in water is very, very small. So that is why, if we think back when we talk about in Chem 1, we said water does not dissociate. Now we have to modify this statement a little bit. Water does dissociate, but it dissociates in a very little amount. All right, so from this concentration, we realized that since water is a neutral species or neutral substance, so anything that has water and we call it neutral, like a neutral solution, the concentration of these two ions, hydronium and hydroxide, must be same. I like to point out, at 25 degrees, they both equals to 1.0 times 10 to the negative 7th molar. Keep in mind, Kw is a function of temperature, which means as temperature changes, the value of Kw change. Which also means, keep in mind, the concentration of hydronium hydroxide in the neutral solution may not be 1.0 times 10 to the negative 7th if temperature is not 25 degrees. But nevertheless, the concentration of these two ions must be equal so that we can call it's a neutral solution or neutral system. All right, so once we understand all of that, for acidic solution, it is hydronium that dominates. So that means the concentration of hydronium must be greater than that of OH minus. So if we apply to the value, so hydronium concentration must be greater than 1.0 times 10 to the negative 7th. Of course, that's at 25 degrees Celsius. And for a basic solution, it is the OH minus term. So that means OH minus must have the concentration greater than 1.0 times 10 to the negative 7th. On the other hand, hydronium must be less than that value. So we find out OH minus, the concentration must be greater than H0 plus before we call the solution basic. Now let's look at two examples. Our first example, so the concentration of hydroxide in a sample of seawater is 5.0 times 10 to the negative 6 molar. The question wants us to figure out the concentration of hydronium and also wants to know what kind of solution this one is, acidic, neutral, or basic. Okay, for us to realize this type of calculation problem, we know or we see both OH minus and hydronium mentioned in the same question. That means we have to use Kw, because Kw is the only equation only equation that have these two combined. Well, you may have a question. Under what circumstance can we use 1.0 times 10 to the negative 14th for the value of kW? Okay, so this value is by default. That means we can use kW with this value, 1.0 times 10 to the negative 14th, unless we are told otherwise, or the temperature is no longer 25 degrees Celsius as we specify. For the rest of cases, feel safe to use the value of kW, 1.0 times 10 to the negative 14. All right, so according to the question, we know the equilibrium concentration of hydroxide is 5.0 times 10 to the negative 6 molar, and kW is known, hydroxide concentration is known, so the concentration of hydronium can be solvable. So throughout a series of calculations, we find out it is 2.0 times 10 to the negative 9th molar. All right, so I'd like to highlight right here. So this is the concentration of hydroxide. This is the concentration of hydronium. One is -6 and one is -6. So which one has a greater value? Of course, hydroxide. So there's more concentration hydroxide than the hydronium. So the solution is basic. The reason why I pick up this question is I just want you guys to know our seawater is basic. That is critical, because if seawater is acidic, like what we experience in now, acidification of seawater, so they cause a lot of biological problems like bleaching of a coral reef. Once coral reef is dead, there will go like at least 40% of a marine species. So I just want you guys to realize how important it is about pH, not just in our body or biological beings, and also for our surroundings. All right, our second question is, now we have a different temperature, right? So at a 50 degrees Celsius, the value of kW now becomes a different value. It says 5.5 times 10 to the negative 14. So it's more than 5 times over. What are the concentration of hydronium hydroxide in a neutral solution at this temperature? Again, as we see, both species are mentioned in the same question, meaning what? kW, of course. And another thing that we know from this question, a neutral solution. Neutral solution means these two must have the same concentration. What is equilibrium? Because equilibrium has been long established in this moment as we speak. So we do not have to think twice whether there's going to be an initial or equilibrium. Okay. So when we pick up a sample already reaches equilibrium in terms of acid and base. So it's always equilibrium concentration. All right, so since it's a neutral, so they equal to each other, so we can put x to it. So according to kW, so that's x squared equals to 5.5 times 10 to the 14th. Taking the square root, so we realize both concentration hydronium hydroxide is 2.34 times 10 to the negative 7th molar. If you recall, at 25 degrees, the concentration of hydronium is 1.00 times 10 to the negative 7th. So with a temperature 25 degrees higher, the concentration of hydronium increased by the factor of almost 2.5. So imagine if we have a seawater, okay, so in the area of the equator on the sea, so it is quite common under the sun in the summer, so the seawater on the surface could reach about 50 degrees Celsius. At this temperature, there is more hydronium than in seawater that is only about 10 feet down. So imagine if this concentration of hydronium going down as in the seawater, coral reef cannot survive under this concentration. So that is why, okay, so in a certain real area of oceans, there's nothing. There's no coral reef or whatsoever because of this. So that's why we call it desert of the sea. I just want to let you know. Before we leave this slide, one thing I want you guys to realize. When we talk about the neutral solution, the concentration of hydronium and hydroxide must be equal and always equal. It doesn't matter what value that comes up. Okay. It could be 1.0 times 10 to the negative 7, or it could be some other value like 2.34 times 10 to the negative 7. It doesn't matter. As long as it's neutral, these two concentrations must be equal. It just happened to be 1.0 times 10 to the negative 7 if temperature is 25 degrees Celsius. All right. So from the definition for Kw, we now realize Kw equals to the concentration of hydronium times the concentration of hydroxide. So that means we can replace the concentration of hydroxide with hydronium, right? So for example, if we have a very basic solutions like 10 mole of a KOH, 10 mole of a KOH means 10 mole of hydroxide. According to the Kw, so the concentration of hydronium should be 10 to the negative 15. So that gives us a very wide range of concentration of hydronium to speak of. For example, 10 mole of hydronium, like concentrated hydrochloric acid, all the way to the very concentrated strong base like potassium hydroxide solution. So all of which can be used the concentration of hydronium to represent. All right. When we talk about the concentration for acid and base, okay, sometimes also neutral 10 to the negative 7, 10 to the negative something something, it is not that easy for us to represent or communicate with others. So people come up with the idea. So how about we put a P in front of H? Okay. H stands for hydrogen, so H plus. Okay. And remember, in the early of the 1980s, H plus has been replaced by the hydronium H3O plus. So the pH now, the newest definition is pH equals to negative log of concentration of hydronium instead of negative log of concentration of a proton. So nowadays, this definition is much more common, but I also want you guys to know what is the original definition of pH, because for people with my age or older, so they still use proton instead of hydronium. I just want you guys to know. So later on, if you see some old guy talking about protons in a solution, actually they mean hydronium. Okay, so now let's say we got an acidic solution. Okay, so hydronium has a concentration 0.1 molar. If we take negative log of a 0.10 into our calculator tells us it's 1.00. So this is what the pH value of this acidic solution. Okay. So from this, we suddenly realize it's become a lot easier for us to describe the concentration of hydronium in a very compact value, the value of a compact value like from 1 to 14. So this is the pH values of some common substances that we have seen, okay, in our lab. So for example, in our lab, we got 1 mole of HCl. Okay, so negative log of 1. Remember, log of 1 is equal to 0. So Well, for 1 mole of HCl, pH is 0.0. Our stomach acid is 1.0 to 3.0. I believe our stomach acid is towards 3.0. 1.0 is something that we can see to certain species of vultures. I don't know if you heard about the vultures can even eat bones. Why they can eat bones? Because so once they have the bones in the stomach, since the acid is so strong, they can dissolve bones. So that's why the vulture, okay, they can eat some rotten meat, because with this acidity, nothing can survive. And look at the lemon juice. The pH is very, very low. Okay, how low? In about the same scale as our stomach acid. When I look at this, I refuse to drink lemon juice, especially before sleep, because that thing is going to be very bad to our teeth. Okay, I didn't realize beer is acidic. As you can see, okay, so if you have something in the pink range, that is what we call the acidic. All right, so if you have something in the blues, that's what we call the basic. So for example, milk of magnesia is a 10.5, so very basic. Okay. And for the household ammonia that we use to clean up the surface or in our laundry or the bathroom, so it's 11.9, it's quite basic. Lye is the most basic substance we can buy from grocery store, so it's a 13.0. So 13.0, that means 0.1 mole of hydroxide. So for 1 mole hydroxide, so that is 14.0. So from this scale, we suddenly realize that for neutral solution, pH is equal to 7. Why? Because at 25 degrees for water, the concentration of hydronium is 1.0 times 10 to the negative 7, the same as that of hydroxide, as we know. So if we take a negative log of hydronium, so that's 7. Water is neutral, so any neutral solution with a water solvent should have pH of 7. All right, so as for acidic, as you can see, it's in the pink area, so they must have a pH less than 7. And for the basic solution, they must have a pH that's greater than 7. The higher the pH, as you can see, it is not a higher the concentration of hydronium. It is the opposite. Okay. So the higher the pH, the more basic the solution is. That means the higher the concentration for hydroxide, suppress the concentration of hydronium, on the other hand, so the lower the concentration of hydronium. Of course, if we reverse that statement, okay, focusing on acidic solution, so the lower the pH, okay, so as we can see, if we have lower the pH right here, and the more acidic a solution it is, and the higher the concentration of hydronium, meaning the lower the hydroxide. So the trend of a pH and that of concentration of hydroxide is totally opposite. The higher the pH, the weaker the acid, the lower the concentration of hydronium. This is something that I want you guys to get used to. All right, so once we have the pH, how are we going to get the concentration of hydronium? So here's the equation. So we take the 10 to the negative pH. One thing I'd like you guys to realize, if a pH changes by n unit, the concentration of hydronium changes by the factor of 10 to the negative nth. So for example, okay, 1 mole of concentration, 1 mole of HCl has a pH 0.0. 0.1 molar of HCl has the concentration as a pH of 1.0. It doesn't sound too much, right? It's a change only by the 1 unit of a pH. Look at the concentration of hydronium. The one is 1 molar, the other one is only 1/10 of that. It's 0.1 molar. So if we change the pH by 1 unit, the concentration of hydronium can change by a factor of 10. Okay, factor of 10. So this is how serious it is. Okay, so when we use a pH to represent the concentration of hydronium of the solution. Okay, before we leave this slide, a few things I want you guys to realize. So first, the definition of pH. How do we realize the acid, the basic, and the neutral solution with respect of their pHs? And the relationship between the pH with the concentration of hydroxide, that of hydronium, and how we're going to get concentration of hydronium back if we know the pH. So a lot of things that we need to know from this slide. All right, so once the pH is introduced, people find out, okay, so if pH is negative log of H plus or hydronium, why can't we use a P for something else? Just simply say P is the negative log for whatever that follows. So for example, pH, right? So we have discussed that. Or we can use the pH. So POH is the negative log of hydroxide. So that means if we want to have the concentration of hydroxide back, all we have to do is attend to the negative POH. And then we can have a pK. pK means negative log of K, the equilibrium constant. All right, so once we know what the pK means, this is something that's quite interesting I'd like to discuss a little bit. So for example, pKW. Remember, P is negative log, right? So that equals the negative log of Kw. What's the value of Kw? 1.0 times negative 14. After taking the negative log, it's a 14.00. That is a constant, right? At 25 degrees, everybody knows. But on the other hand, definition of Kw is the equilibrium concentration of hydronium times that of hydroxide. And what are we going to do here? We're going to P it. So pKw equals to P of this product of concentrations. Remember, P is a negative log, right? So if we have a log of a product, that is equal to the sum of the two logs. So we can, okay, so can separate this hydronium and hydroxide into this with a negative log of hydronium plus negative log of hydroxide. Negative log of hydronium, that's pH, right? Negative log of hydroxide, that is POH. So pKw equals to pH plus POH equals to 14. That is another important equation that we need to know. What does that mean? It means once we know the pH, we know POH automatically without we have to ask anybody. By default, temperature is 25 degrees. So pKw could be different, the value could be other than 14.00 if we have different temperature. But if temperature is not mentioned in the question, default value of pKw is a 14.00. The lower the px corresponds to the higher the value of x, remember? Okay, so it's a negative log, so the trend goes the opposite. So the smaller value of p something, that means the higher the value of that something. Okay, so one of the experiments based upon my experience in the Chem 1 lab is titration. I don't know if you agree with me or not, but I found that most of students enjoy it for titration. So during the titration, okay, so people will try to make solution colorless to pink, right? So the thing that changes color is what we call the indicator. So the indicator here is a substance that changes color in a very specific pH range. Okay, so one way for us to look at the indicator, so that is the form of its conjugated acid. So we have an acid form of this indicator, and it undergoes dissociation, as you can see. So once it undergoes dissociation, so for its conjugate base, it is a conjugated base for an indicator, it shows different color. So that is why we see the sudden color change. So it tells us whether that is going to be the end of our titration. So for indicator, it's just a pair of conjugates that shows different color at a certain value of pH. So far we have many indicators. Okay. So a lot of fancy names right there. And I just want to point out that the most common indicator that we use in our lab is phenolphthalein. As you can see, the color changes to the pink right here when pH is somewhere between 8 and 9. Okay. So it's a little bit past 7, but that is still accurate enough for us to call the end of the titration. This is something that we're going to discuss a little bit more in our next chapter when we talk about the titration curve. All right. So once we have all this pKw, kW, pH discussed, now let's focus on strong acid and the bases. Okay. So how are we going to characterize strong acid and base? We characterize them by the number of protons and the compound can provide or the compound can neutralize. Neutralize means it's a base. So such concept is called proticity, the number of dissociated or ionizable protons. Okay, so for acid, we talk about number of protons of an acid that can contribute to the reaction. For the base, there will be the number of protons that can be neutralized. Of course, with OH minus as you may. Alright, so if you have a formula that only has one proton, so we call such acid monoprotic. Remember, we have 6 strong acids in our discussion of a definition of acid and base. Okay, so last 3 binary acids in the group 7, so HI, HBr, and HCl. And also we have 3 oxo acids where we can find the difference of subscripts from hydrogen and oxygen greater than 2. Right? So for chloric acid, 4 minus 1, that's a 3. Nitric acid, 3 minus 1, that's 2. So we have all the strong acids. Okay, since all of them has one proton in their formula, so we call them monoprotic. And of course, we can have strong bases as well, meaning they carry only one hydroxide per formula. Since there's only one hydroxide, so the cation must be alkali metal. So we got lithium hydroxide, sodium hydroxide, potassium hydroxide, sodium hydroxide, cesium hydroxide. All of them will give up 1 unit of hydroxide from that formula. All right. As for dissociation, okay, so what I like to point out here is it's a single arrow. Single arrow means 100% of dissociation. Since it's 100% dissociation, and that goes the same with the base as well. So the equilibrium concentration of hydronium for the acid, hydroxide for the base will be equal to the initial concentration of this strong acid or strong base. So that is very important for us to realize how we can relate the concentration of acid to the concentration of hydronium or hydroxide in the cases of strong acids or strong bases. All right, so first we need to know just how many strong acids, as we call the monoprotic. How do we know the concentration of hydronium if we know the concentration of acid? And how many strong base we call the monoprotic? And how do we get the concentration of hydroxide from the concentration of those basic solutions? So these 4 are very important for us to realize, okay, for the strong acids and strong bases. Okay, so if we talk about the monoprotic, that could be as well. Diprotic means two dissociated or ionizable protons. There's only one strong acid, H2SO4. And strong base, okay, so that could be hydroxide, okay, with the cation of alkaline earth metal. Okay, so as we already discussed, since they are strong, so for strong acid, so this is going to be 100% dissociation. Okay, so just how do we know the concentration of equilibrium from the concentration of acid? Is that going to be 1 or 2? From this balanced equation, it's obvious for 1 mole of H2A, which is a strong acid, it's going to give up 2 moles of hydronium. So that means the concentration of hydronium is going to be twice as much of the diprotic acid. Okay. So I just want you guys to realize where we put this 2. Okay. For strong base, same argument. The concentration of hydroxide is going to be twice as much of the basic solution. Okay. And so very similar. Okay, so how do we recognize strong acid? How do we know the strong bases? How do we connect the concentration of hydronium or hydroxide with their initial concentrations of solutions? So these are the points that we need to know about the strong acids and the bases. One last thing. Assume equal concentration. So for example, same concentration of H2SO4 and HCl. Say they all 1 molar, they're both 1 molar. So HCl monoprotic, so hydronium is 1 molar, right? For sulfuric acid, H2SO4, there's going to be 2 molar of hydronium. So with the equal concentration, the more proticity of an acid, the more hydronium concentration. Since there's more concentration of hydronium, the pH is lower. So this is something that you're probably going to experience later on in your homework assignment. All right, now let's take a look at our next example. Okay. So in an art restoration project, we have to prepare 2 solutions of nitric acid. So one is 2.0 molar, one is 0.0063 molar. All right, so question wants us to calculate the concentration of hydronium, hydroxide, pH, pOH of these 2 solutions at 25 degrees. How important it is at 25 degrees, by the way? Yes. We know the value of Kw. All right, so again, we see the hydronium, hydroxide in the same question, we call Kw. But before we do that, remember we have talked about the strong acid and strong base, and you may guess our next section would be weak acid and weak base, which is the most important topic for this chapter, right? So before we carry out any calculation, I just want you guys to realize, okay, so we need to identify the acid and the base. We need to know whether such acid is strong or weak. Okay. And that is important because we're going to follow that procedure for every single calculation. First, we need to know whether it's strong or weak because they have a total different way of calculation. All right, HNO3. So we understand it's a strong acid. Since it's a strong acid, according to the formula, it's a monoprotic. So we know it's going to be 100% dissociation. Concentration of hydronium is the same as the concentration of nitric acid. So this is how we get the concentration of hydronium from strong acid. Strong base, the same thing. Okay. For strong base, it is not hydronium, it's hydroxide, of course. All right. So for weak acid and base, okay, we're gonna set up our table, which is something we're gonna discuss in our next section. Gonna cost us a lot of time here. All right. So like I said, this problem calls for Kw or pKw. So we have pKw equals to pH plus pOH equals to 14.00. 3 line here means always equal at 25 degrees, of course. And we pull out the definition of pH, definition of pOH, and how we can get the concentration of hydronium if we know the pH and so on and so forth. And we may need all these equations for our calculation. Now, in first question, 2 molar of nitric acid solution. Because it's strong acid, as we know, so the concentration of hydronium is going to be 2 molar. Alright, so once we know it's 2 molar, so we can calculate pH. Negative log of 2.0 is something negative. It is okay. It is quite okay for us to have a pH that is negative. That means the acid is too strong. Alright, so for pOH, pOH equals to pKw minus pH. Okay, pKw is a 14, so 14 minus pH. Carry it out, it's a 14.30. Okay, so for strong acid, it's quite okay for us to have a pOH that's greater than 14, vice versa. For strong base, it's quite okay for us to have a pOH that's negative, pH with a value greater than 14. Okay, so it's perfect. Okay, just don't set up from 1 to 14. That has to be the value of a pH. No, that's not the range of the pH. pH can be any value, negative or positive, depends on just how strong the acid or base is. Alright, since we know what the pH is, so we can take a 10 to the negative pOH in order to get the concentration of hydroxide, and we figure out it's 5.0 times 10 to the negative 15. And by the way, okay, Kw equals to concentration of hydroxide times that of hydronium can also be used. So since we know the concentration of hydronium, so hydroxide can be known as well. So the same. All right. So in our second question, still it's just going to be a strong acid solution. Okay, but only this time the concentration has changed from 2.0 to 0.0063. Now the pH looks quite quote normal unquote. Okay, because it's in the range of 1 to 14. But I want you guys to have an open mind. For some strong acid or base, it's okay for us to have a value that's negative or value greater than 14. So that's perfectly okay. All right, so pH is 2.20. So pOH is going to be 11.8. So OH minus 4.6 times 10⁻12 mole. That is the end of this section. Okay, so in this section we talk about self-ionization of water, because water, according to BR's definition, can be acid and base. So dissociation or the transfer of the proton. So we introduce Kw. From Kw we talk about pH, and from pH we talk about how we treat strong acid and strong base. All right, so that's it, and I'll see you guys in the next section.